Oh, that's really fun and pretty terrifying. Today, we're gonna see how laser cutters like these are made. I'm here at Thunder Laser in Dongguan, China, and they've been super generous to fly me out here and give me access to their factory. Now, I thought I knew what laser cutters like these were capable of, but I've been blown away by what these new machines can do, some things that I didn't know were possible. Let's go take a look at the first step in the process. The first step in the process is to make the enclosure of the machine, which is made out of sheet metal. It starts as these big sheets here and gets cut down into these individual pieces by this giant fiber laser back here. Let's go take a look. This is the business end of the laser. This is a 6,000 watt fiber laser, which is perfect for cutting sheet metal like this. Super accurate, leaves a very narrow curve, so it only takes out a tiny width of material where it's cutting. They're cutting flat patterns here. We'll see in the next step how they bend them into three-dimensional shapes. They've got two different beds here, so they can be loading and unloading one on the back side while they're cutting on this one. Makes it super efficient. Next, they bring the cut parts over here to a sheet metal bending machine, sheet metal brake. This is a CNC sheet metal brake, so it's all computer controlled, and he knows exactly where to put it, and then the machine knows how hard to push on it, and there's like a jig that bends it at the right angle. So right now, he's already partway through the process. They've already bent the sides, and they're bending the ends on. So he's going from that to this. So he's bending the ends on here in two bends. You know, you can see probably here, there's some box fans. They're gonna get attached here. You know, like a computer fan kind of deal. So these would be the four mounting bolt holes. And obviously, you can see they can bend stuff that's super wide or quite narrow, just depending on how they set the machine up. Let's head upstairs, see the next step. They bring the bent parts up here to start tack welding them together into full enclosures. So he's got a TIG welder here, and he's just doing very careful fit up and just tack welding each of these little spots and making sure that the two edges meet perfectly. So he's got each of his pieces, knows how they go together. They've got like 3-4 stations here doing tack welding. So he's tacking things in one spot and then kind of hammering them into place. He's got a hammer here. He's also just using a pair of pliers to beat things into place, tacking them as he goes along, being really precise so that everything lines up. But these tack welds aren't enough to hold everything in place permanently. So here he's got a fiber laser welder. Right now he's welding on little tabs with holes. I'm gonna try and avoid looking in this. Nobody's wearing welding masks here, but just tacking in place the various little fit-ups for putting bolts through and things like that. Boy, those laser welders are impressive. I've seen these before, but man, they are clean and easy to use. Like a hot metal glue gun, but really precise. So this guy's got a laser welder as well, and same deal. He's adding just little brackets and things, these little angled bits. Finally, they bring the fully welded pieces over here, and he just hits all the exterior welds with a grinder to prepare them for powder coating, which happens at another nearby factory. Let's head over there and see how that works. The first step at this factory is all the parts get put in this basket and lowered into an acid wash for about 80 minutes, I was told. The acid removes any oils, rust, any other contaminants, so that the powder coating and the putty that we're gonna see next sticks really well to the metal. Then they bring the parts over here, and she is putting on putty. On the can it says polyester putty, but she's filling every little divot and hole and crack and imperfection so that the finished case is beautiful and flat and perfect. Once the putty is dry, they're now using palm sanders to sand everything perfectly smooth. And this is the last step before it goes in for powder coating. This is the powder coating booth. It's a pretty cool process. It's a dry powder that comes out of the gun, very, very fine mist of powder. And the gun is electrically charged, the opposite charge from the piece. So the piece attracts the powder to it, and sticks to it. And it's a very light coating. If I touched any of this with my fingers, it would immediately come off and I would ruin it. They'd have to clean it and start over. And you'll notice he's just kind of spraying it in the general area. It's not like spraying paint. He's just trying to get full coverage on it right now. There's no wet, there's no stickiness, there's no glue. It's just a powder sticking to an electrically charged surface. Now, obviously, if I was hanging out here for any amount of time, I'd want a respirator on like he has. The parts head into a 210 degrees Celsius oven, and that melts the powder coating and bakes it onto the surface of the metal. Let's go see them come out the other side. After about 20 minutes of baking, they pull out the finished baked powder coated parts. Now, obviously they don't change from blue to white. It's a different batch. Whew, it is still quite hot. Even back here, it's like making me sweat. So they'll let these cool down and then they'll take them to the next room for assembly. This is one of the finished powder coated parts. You can see this nice little pebble texture on here. I'm sure you've seen this on 1,000 machines, but it just looks really pro. The pebbling helps hide any imperfections, but you can also see this thing is just like dead flat. The corners look nice and sharp, and that's from all that putty and sanding that went on earlier. So this is ready to go to be assembled into the finished cabinet of the machine. Let's go take a look at that. Here they're bolting together all the pieces into a finished enclosure. We're about at the end of the day here, so they're pretty much done with the units they're working on, but they're just fitting up doors and making sure they fit properly and whatnot. But these enclosures are made entirely of sheet metal parts. There's a few small pieces of tubing in it, but there's no underframe. It's all a bent sheet metal frame that's stacked up out of different parts. They're just bolted together by sheet metal screws and bolts. Over here you can see this one's partially put together, so it's got two pieces. They're not put together yet. I guess this is the bottom unit. So this is where the casters go. There's some big bolts the casters screw up through. He's just cleaning out holes. It looks like there's a powder coat that melted into the hole, so he's just coming in and touching them up. Once they're done here and they're looking good, they've got the lids on them. Over here they're putting on the acrylic for the glass windows. Once they're fully assembled here, they get wrapped up in plastic and sent to the final assembly factory. Let's head over there and we'll see how they build it out into a full laser machine. These are the finished enclosures coming from the sheet metal factories and headed upstairs to have all the parts assembled into them. In back here is the parts warehouse where they're storing parts coming in from other suppliers. But up front in this little area, they're assembling these sub-assemblies. This is a bracket for holding the laser tube in the back of the machine. They're big on standard operating procedure here. So up here is all of the instructions and information about the correct way to assemble each of the parts that get assembled here. Here are all of the bolts and springs and things for assembling those parts. They're all labeled. There are certain, check-offs and things that need to be checked for each part. And then the parts go in these blue bins here, which are labeled with, what part they are, what machine they're for, and they get inventoried back into the parts warehouse before they're taken upstairs to be assembled into final machines. So let's go take a look at that. So far, everything we've looked at is the steel enclosure of the machine. This is the area where they're making all the precision aluminum parts for the inner workings of the machine. So this is where the aluminum stock comes in from the aluminum extrusion factory, and then over here it gets cut. Here they're cutting the bar stock down to stock of known size. This is a CNC saw, so it's operating totally automatically. He's just kind of overseeing it and checking lengths and stuff, but it's cutting to a set size on its own, which is pretty cool. I've not seen one of these before. Definitely saves a lot of labor. Next, we'll go see where they machine this raw stock into parts. Over here, there are a number of CNC mills. They actually brought this in-house. They used to send it out. They said they brought it in-house to improve quality and precision. They have more control over the process here. They're making little parts like this. This is part of the head. It holds the nozzle and the tube on the laser head. And you can see this needs multiple setups. So, mill it once like this, maybe once like that to get the full thing milled. There's also some manual mills over here. There's a couple drill presses. They're trying to do as much in-house as they can now just to control quality. This is where everything finally starts coming together. We've got the sheet metal case enclosure that was assembled up at the other sheet metal factories. We've got the aluminum parts that were machined and assembled downstairs. And now the assemblers are starting to assemble it into a final machine. So this is the first step. This is mechanical assembly. He's putting in place rails and covers and lots of bolts and nuts and screws and aligning things. And one of the things that they've done that I really like is these jigs that they've laser cut out of acrylic for all their nuts and bolts, so that the assemblers can know exactly how many bolts they need to put into a given machine. So when they start an assembly process, they fill this jig up and they know if they still have bolts left, they've missed one somewhere. The other thing I really like is that they have these trays laid out with all the cutouts for their tools, so they're not leaving tools behind in machines that are getting shipped to customers. Very smart. Once the mechanical assembly is done here, they go install the electrical pieces. This is the cable assembly area, and they're putting together all of the custom cables that go in the machine. So color-coded with the right connectors, right lengths. You know, this is a pretty varied process depending on what cables they're making at the time. They're making batches. Over here, she's cleaning off cables that have just been stripped. They have some powder and lubricant and stuff in them. She's stripping the ends of cables by hand. And then over here, she's putting on cable markings, these sleeves that indicate which cable is which. They've got a bunch of different wire strippers and heat shrink and cable markings and heat guns here. These are automatic crimp machines. So these are for spade connectors here. You stick a cable in, you hit a foot pedal, and it goes crimp, and then you go to the next one. For anyone who's done this by hand before, these are just like a miracle. I wish I made enough cables to justify owning one of these machines. They're amazing. Blink of an eye, and it's all the connectors are just on reels here. And then down here, he's soldering two cables together that are twisted together, and then putting a crimp on the end and some heat shrink. And then they're storing inventory for all their cables in these bins. So this is a particular cable assembly. These look like they might even be half finished because this end doesn't have anything on them yet. But they're tracking all their batches and their part numbers and stuff here. They've also got stuff hanging over here on these racks. These are sleeves to go in screw terminal blocks to make it easy to put the wires in the terminal block. This kind of stuff really helps with standardization and making sure every machine is wired correctly and looks nice and neat inside. This is one of the coolest machines I've seen in all of China. I've seen these before. This is an automatic cable cutter and stripper, but this one does something I've never seen before, which is it also puts heat shrink labels on these. So the white is a piece of heat shrink that has printed on it N3 for this particular batch. So the wire comes in this side through this series of rollers. It's getting cut and it's getting stripped to a precise length. On this side is the white heat shrink tube, and it's coming in here and getting printed right here with whatever label they program in, cut to size, and then it gets brought down by an arm. The wire gets stuck through it and cut. And so when they go to assemble this, they'll pull off the part that was stripped, put on a crimp, and assemble the connector. Super cool, huge time saver if you're making hundreds of cables. This is where everything electrical is being added to the machine. So circuit boards, power supplies, controllers, switches, limit switches, and then all of the custom cables we saw being made downstairs are being run between each of those. And they're trying to make it look neat and tidy so that it's easy to maintain. Let's go take a look at the far one. The guy's pretty far along on that machine, and we can kind of see how this all works. Come with me. So he's kind of tucked back in the corner here. It's a little bit hard to see, but you can see control board, power distribution, and then he's got these cable trays running around it to keep everything nice and tidy. So one, they can easily inspect and make sure it was wired properly. But two, if anything needs to be debugged or repaired in the future, it's easy to figure out what goes where, swap out parts, swap out cables. And then he's got all of the connectors he needs, all of the tools. There's wiring diagrams on a clipboard here. And then this clipboard has the inspection sign-off sheet. As it goes through the various stages of manufacturing in the factory, it gets signed off by various people, both the worker and then I think a manager also signs off. This will follow the machine through the factory. So here they're making the serial number plates to go on each machine, and obviously these have to be custom per machine. So they've got the serial number, but they've also got the type of laser, power, weight, manufacturing date, They're using one of their own fiber lasers, which is their Aurora series. It's a galvo head, so it's very, very fast. This is an aluminum plate that's been anodized black, and then the laser removes the black to reveal the raw aluminum underneath and make the markings. Now, obviously, if this is running in production, they're running with the lid closed. I get a lot of comments in my videos like, oh, this is totally unsafe. It really isn't that unsafe. If you were putting something under here that you were worried about being reflective, maybe, but honestly, with a fiber laser with metal underneath, pretty darn safe. I shouldn't be waving my hand underneath there, but outside of that, it's really quite common to see these out in the open, and yes, technically you're supposed to have the lid closed, but it's really not a big deal. This is the laser tube testing and burn-in area. Hands down, it's one of the coolest rooms in the factory. Behind me here are a bunch of glass tubes that are in the burn-in phase. So when they receive the tubes from their supplier, first they put them on a test bench, test the output of the laser, then they stick them on this burn-in bench for 8 hours and run them. The laser goes out of the front. The front is towards the back of the bench here, and they've got them pointed at these giant graphite blocks, which are acting as heat sinks. And I'm being pretty careful where I wave my arms because this has high voltage here just via this alligator clip into the tube. And then the beam out of the front of the laser tube is invisible. And it's quite a bit of heat going into that graphite block. So they do testing, then an 8-hour burn-in, then testing again to make sure power hasn't dropped. Then for the glass tubes, they shelve them for 15 days and then test them again to make sure that the power hasn't dropped. And that really helps with premature failure, which can be a real problem for lasers that come from other manufacturers. These tubes are not cheap, a couple grand each, and having to replace one early really increases your cost to own a machine like this. Over here is the burn-in area for the RF tubes. Again, they test them on the bench, run them for 8 hours, put them back on the test bench, and make sure there's no change in output power. These are just so cool. The laser beam in the middle, I don't quite understand why it's visible inside the tube, but not once it's out of the tube, but it looks like one of those plasma balls. And these are a gorgeous piece of glass with all the coils and the cooling. It's incredible. The guy that runs the testing in here was showing me that he's got an easy way to test that a laser is putting out output. Okay, that's pretty bad. That's pretty awesome. Oh, that's really fun and pretty terrifying. Let's go try that at the RF tubes. I'm being very stiff because I really don't want to hit anything here. It's pretty tight quarters. Oh, wow. Okay, this is actually really cool. You can see the difference between the glass tubes and the RF tubes and why these RF tubes are so much better. The spot size for the RF tubes is much smaller. Do you see how narrow that is compared to this? This is why RF tubes are so much better. You get a much finer cut because you're starting with a narrower laser beam that's more tightly focused. Wow! Okay, this is just a great example. This is the RF tube, this is the glass tube. Look at the difference in those. That's amazing. So you're starting with a much smaller, tighter laser beam, and it just plays through the whole process. Sure, it does get focused, but when you're starting with something that's already tighter, it's that much easier to get a really, really thin, precise beam. Thunder Laser is moving towards having all of their machines have RF tubes and getting away from the glass tubes because of this. Now, it used to be that machines that had RF tubes were $100,000, and one of the things they're doing is really democratizing it by bringing that price down so that, you know, everyday mortals like you and me can own a machine with this kind of tight beam and high quality. Once the machines are all wired up and the tubes are tested and burned in, everything comes up here and they install the tubes into the machines. This one here is the glass CO2 tube. They said they're a little bit short on RF tubes today, so we can't see one of those being installed, but it's a very similar process. This gets mounted on some V-mounts in the back that have rubber on them, and then like a rubber or silicone strap over the top. Obviously, you don't want to create any pressure points or sharp points on the tube that might cause it to break. They're pretty expensive. Once they install the tube, then they do testing in the same location. And they've got a couple cool setups here. We'll go look at a machine that is in testing, but they actually have cooling pipes on the back here for the water cooling that goes to a central cooler at the end for the glass tubes. The glass tubes need an external water chiller, whereas the RF tubes don't, which is one of the really nice advantages of the RF tubes. Once they get the tube up and running, then they need to align the optics. Let's go take a look at one of the machines that's a little bit further along. So next, he's aligning all of the optics of the machine. So lenses, but mostly mirrors. So the tube's in back, and it's getting bounced through a two-way mirror along with a red visible diode laser, basically like a red laser pointer that's on the same optical path so you can see where on the material you're gonna cut. And then through a series of mirrors to bounce it to this mirror here on the arm, and then out to the head and down the tube. And what you want is you want to align each mirror so that the laser path is going down the middle of whatever hole the path of the laser is supposed to be going through. The process for this, super simple. He's got just a roll of paper tape. He's putting a piece of tape on the hole, firing the laser, seeing where the singe mark is, and adjusting. There's some brass adjustment knobs that he's tweaking on the mirror to adjust the position of the mirror to make sure that it is right on center with where it should go. So this laser machine is now in the testing process, and they've developed a pretty extensive testing checklist of a whole bunch of different tests and calibrations they run that all have been based on customer feedback, issues customers have had, issues they've seen with machines that aren't working quite right, to make sure they catch them before it goes out to a customer. So right now he's running number 7 of this set of tests here, and this is the scanning compensation test for, I believe we've had some translation issues, but I think what's happening is we're compensating when you're doing raster engraving, where you're sweeping back and forth and engraving. You want your forward motion and your reverse motion engraving to be exactly aligned, and it needs to be tweaked for various speeds. So they do this test here at 200 millimeters a second, 400, 600, and so on. And the goal is they're making one line in a forward direction and then one line in a reverse direction and so on. And they're figuring out exactly what compensation they need so that the forward columns are perfectly in line with the reverse columns. And then once they figure out what those numbers are for this machine, they engrave them on a separate card that they ship with the machine so that if the customer ever has to reset those numbers, they have a hard copy reference to work off of. But there's, I don't know, 10 or 20 machines in this area that are all in various stages of this testing process. So this machine is now in their 8-hour burn-in period. This is the mechanical run-in. They'll just have it doing various motions for 8 hours, make sure that nothing has premature failure. You know, there's no motor that burns out in that time or a bearing that gets stuck. It's all about reducing failures of the machine once it gets to the customer. The finished machines come down here to be packed up, crated, and shipped out. So they've got all the accessories here, air compressor, fan, and the ducting, toolkit, some sample materials. They put foam corners on it, wrap it in plastic wrap just to make sure it's not gonna get dinged or scratched. Then they build a crate around it. These are custom crates. Put some packing foam around it, put the lid on it, and it goes out. They're just keeping them out here in a tent until they've got enough to fill a shipping container. The shipping containers go to their warehouse in the US, where they ship direct to customers from there. Right now they have one machine that's back ordered. I think the Nova Plus is back ordered. They're catching up on stock. So those are getting shipped direct to customers. But they said they can get better quality in the shipping and less damage in shipping if they do shipping containers to a warehouse in the US and then ship to customers from there. We're now back at the Thunder Laser headquarters in their lab. And I'm here with Shannon Hoover, who's a good friend of mine. We've known each other since the beginning of Strange Parts. And you have an interesting relationship with Thunder Laser.
Yeah, so I'd met the owner, one of the founders of Thunder Laser here. I'd gone on a factory tour. And when it came time to upgrade the machine in the makerspace, I thought of Thunder Laser. The thing I loved about it is that, as you know, in makerspaces, if there's a way to break a machine, somebody will figure out how to do it. These machines were harder to break.
Yeah.
They were safer, they were more reliable, easier to train on. And so yeah, I started recommending them to people. Thunder Laser caught wind of this, contacted me and asked if I'd be interested in working with them. So ignorantly, I said yes, and now that's what I do for a living.
So now you're the exclusive Canadian distributor for Thunder Laser.
Yeah, yeah.
Well, I wanted to grab you because we've seen how this machine is made. It's time to get hands-on, and I figured, what a better person than you. So this is clear acrylic.
This is an 80-watt glass tube. So this one is kind of what the nuts and bolts for laser cutters have been for a long time. Now, the one beside it is an RF tube.
Yeah.
Now, the disadvantage of RF tubes until recently was that they're really, really expensive, right? Yeah. This tube might be $1,000. This might be $10,000.
Okay.
So you can see how the cost of a machine...
For just the tube, not the machine.
Just the tube. This is a 55-watt tube, and this is an 80-watt tube.
Yep.
They have similar cutting capabilities,
okay.
right? And if you'll notice, if you feel this here, the cut is a little bit cleaner on the RF tube as well.
Oh, yeah, totally. Yeah.
On this
what is this mess?
Well, this is kind of funny. This is a diode, and diodes don't cut acrylic. So if you try to cut it, you get this kind of mess.
Just a burned, chip, explodey mess.
Explodey mess. So the big difference between an RF tube from a results perspective is your dot size.
Yeah.
So the laser beam is smaller. Therefore, when it hits the material, you get a smaller dot. If you look at some of the details here on the beard versus this one, it's really like almost no comparison.
The detail on his beard is so much better, and like the lines on his face, it's like 2x the resolution.
Yeah, the other thing that isn't kind of shown here is the time that it takes to engrave. One of the issues with the diode is all the weight is in the head.
Yeah.
So when you're moving the head back and forth,
slamming all that weight around. So you've just got an inertial issue.
Yeah, and so from that reason, I don't think diodes will ever be the speed of either of these types of machines.
Yeah. And I think this sample is also really indicative of that. The detail, but also the kerf width, the width of the cut is so small. Like the lettering here, it almost looks like it would be too small to read, and then you get close to it and you're like, no, it is completely sharp and legible. These are also pretty striking samples. I don't think of CO2 lasers as being able to do curved surfaces. You're either cutting it, burning it, or leaving it alone. And this is very much something else. The scroll work here is amazing, but also just the relief on like his jacket. We're in kind of a lab / demo room environment, right? And there are just samples all along this wall. And half of the stuff on this wall, I didn't realize was possible on a laser. Yeah. I realized when we were walking through and looking at some of this that like, oh wait, like hang on, there's like a step function here of what's possible.
So we've got some material in here. Let me just square it up.
And this is Lightburn here, which is standard, kind of the go-to desktop software for running lasers. So they have a camera here that allows you to align your material. If you're doing something that's not a big sheet of plywood,
that's right,
you can get your design exactly lined up. So this camera is then calibrated against the machine.
That's right. And the cool thing about this camera is you get a top-down view from here, and when I close it, you get a front view.
Got it.
So you can watch your cut happening. One of the other nice things about this is the dual air selector.
Yep.
When you're engraving, you don't want high pressure air, right? Because what that does is that takes your soot and all your particulate and blasts it onto the material.
Oh.
It requires a lot of cleaning afterwards.
Sure, okay.
So I'm gonna send the file to the laser here. So this is going through, this is doing a reverse engrave here. Look at the clean font that you're getting there.
It's gorgeous. It is so clean. I'm so used to when you're cutting or engraving plywood or wood in general, having to like mask it to avoid getting smoke on it. You got all this residue, like you're just dealing with all of these extra pieces, or you're having to sand it afterwards. And like,
I mean, I would still give this a little bit of cleaning. So there we are. So like I said, I would clean up that just a tiny bit.
Yeah, there's a little bit of a smudge there, but like so much less than I'm used to. This is a pass-through?
Yeah.
So you can put a full, so this one here, we could put a full 4-foot wide sheet of plywood in, open the front door, open the back door, and just cut and move it, so we can get 4-foot, 3-foot, 2-foot.
And there's one larger, which because Baltic birch comes in 5x5s, you can slide a full 5x5 into it. So this is the bolt. This is our lowest cost light cutter engraver, 12 inches by 20 inch.
Yeah.
One of the neat things about it is that I can open this bed here. I can override the safety switches, and now I can feed material into there. So I can effectively double the cutting area of this. It doesn't have the pass-through.
One thing you also mentioned, we didn't talk about on the Novas, but we kind of seen it in the manufacturing process, just how accessible everything is. There's doors that pop open on all 4 sides, really. You're gonna have to maintain your machine at some point. You're gonna have to debug something. You're gonna have to replace something. And there's a big difference between a machine that's easy to access everywhere and one that's gonna fight you every step of the way.
The rails are there, just wipe them down. To clean the lenses, just spin these and the lens pops right out. Pull the lens out there, clean it off.
Now, you had mentioned that the bolt machines were really designed for engraving, whereas the Novas are more for cutting.
So there's a few differences. The biggest one is in the head.
Okay.
You notice this head is smaller and lighter.
Yeah.
It still has the autofocus functionality in the back here.
Right.
So there's that tab
Okay,
there.
there's a little plunger, yeah.
Which, by the way, look at this plunger. It bends.
Oh, yeah. Someone got smart.
Yeah. So if you hit it at 1,000 millimeters a second, it doesn't smash everything.
Yeah. Which you're invariably going to do.
Yes. This is an RF tube, 30 watt. So it's a lower power, but really, really like good engraver.
Yeah.
Still has camera. Yeah.
Yep.
The air is indirect. So when you're engraving, you want to push the air away from your material, not onto the material. As I said, when you're cutting,
so you're not just blowing smoke down into your material to stick.
Yeah, that has the low air selector. This allows you just to brush the air away.
Got it.
So even the little bit of cleaning we had to do on that, if we did the same thing on this, you'd basically have to do no cleaning at all.
Got it. What is the largest bolt? Is that the one behind us?
Yeah, so this is the Bolt 32. Again, it's smaller than those. This has a 55 watt tube in it, so you can cut through pretty thick material.
Yep.
This has a coherent tube in, which is a more expensive tube, so that brings the price of this up. It'll really do anything you want.
Okay.
This machine over there, the Bolt, that's about $5,000 US. This one is about maybe 17 or 16,000.
And then what about like biggest Nova, nicest tube?
Like 16 US.
Oh, okay. So we're looking at like 5 to 17,000. And then lastly, real quick, what are these? This is the Aurora line, which is totally different than everything we've talked about thus far. Still lasers, but different.
Yeah, these are galvanometer machines, so they don't have a gantry. The beam moves by a vibrating mirror.
So they've got, just a mirror that it's reflecting off of.
And they engrave like really, really fast and really high resolution.
And different type of laser, right?
That's right. So this is a fiber laser which engraves metals natively really, really well. If you want to do metals on these machines, you have to put an additive like a Surmark product on it.
Yeah.
And it doesn't technically engrave, right?
Yeah.
These ones, we have UV laser sources.
Oh, wow.
We have fiber laser source, and we have the MOPA laser source.
Oh, wow.
The MOPA is really neat in that you can engrave color onto steel, which is a bit of a magic trick. The cheapest one, the lowest cost is the Aurora Light. That one is like 4,000.
If you would like to learn more about Thunder Laser or buy one of your own, go to thunderlaser.com. We'll put links down below and let them know I sent you and Shannon sent you.
Yeah.
I'm just really impressed. Like, this is opening my eyes to another level of what's possible with a technology that I thought I knew and thought I knew the limits of. And it turns out the bar is a lot higher now. I have gotten to see a sneak peek at the newest machine, which is a dual tube laser that is both CO2 and fiber.
Yeah.
And we'll be covering that more coming up, but it's another step function jump. It's very, very cool.
Thunder Laser asked me to mention, in the time since we've shot this video, they are now offering RF tubes all the way from their entry-level Bolt series to their Nova Plus series, all the way up to their new Industrial Titan series.
Shannon, thank you so much.
Yeah.
This is awesome. Thank you for setting this up. I'm blown away. We'll see you again soon.